Hello and welcome to my YouTube channel Innovative Learning. Today we'll be solving Cambridge International AS and A-Level Computer Science Paper 1 May-June 2021. Let's begin. Question 1. Anya scans an image into her computer for a school project. Part A. The scanned image is a bitmapped image. Complete the following table to describe the two terms about graphics. Okay, so the description for pixel is that digital images are made up of pixels. It is the smallest square of one color and it is the smallest addressable element represented as binary. And file header's description is that it is the data about the bitmap image. The data about the bitmap image, which is found at the beginning of the file. For example, header, file version, palette, etc. Part 2. The image is scanned with an image resolution of 1024 by 512 pixels and a color depth of 8 bits per pixel. Calculate an estimate for the file size, giving your answer in megabytes. Show your working. Okay, so for this question, we have to multiply the image resolution, which is 1024 into 512, and let's open the calculator. So 1024 into 512, which gives us 524288. Okay. Pixels. So now this is pixels per byte. Okay. And we need our answer in megabytes. And in order to do that, let me just explain what I'm going to do over here. So we have byte. Then we have kibibyte, then we have megabyte. We need our answer in megabyte, and in order to do that, we have to divide by 1024. If we divide byte, the size of the byte, once with 1024, the answer will be in kibibyte. And then we have to divide it again with 1024 so that we can get our answer in megabyte. So the answer that we got over here, we're going to divide it twice by 1024. And let's input these values into the calculator. And the answer is 0.5 megabytes. Part B. The image is compressed using lossless compression. Identify one method of lossless compression that can be used to compress the image and describe how the method will reduce the file size. So we have to write the lossless compression method and we have to write its description. Okay, so the lossless compression method will be run length encoding. Short form for that is RLE, and the description will be that RLE replaces sequences of the same color pixel with color code and number of identical pixels. Part C. One of the colors used in the image has the hexadecimal color code. This is the hexadecimal color code, and FC is the amount of red, 23 is the amount of green, and 8A is the amount of blue in the color. Convert the hexadecimal code FC into denary. Okay, so first we need to know what are the denary values for F and C. And as you can see from this table that the denary value for F is 15 and the denary value for C is 12. FC is in base 16 number system, and in order to convert FC into denary, we have to take the base 16 numbers weighting, which is basically 16 to the power 0, 16 to the power 1, 16 to the power 2, and so on. Since we have only two values over here, F and C, we will go with the first two, 16 to the power 0 and 16 to the power 1. So how will we do this? Basically, we have to multiply these values like this. So the first one is 15 into 16 to the power 1 plus, then we have 12 into 16 to the power 0. Then we will calculate these values. So 15 into 16, because 16 to the power 1 is 16, and 12 into 16 to the power 0 is basically 1. So 12 into 1 is 12, and the answer is 240 plus 12. So 240 plus 12 will be 252. So the denary value for FC base 16 is 252. Make sure to show all of your working and then write the final answer 252 in denary. Part 2. The amount of green in binary is 001 00011. This has the denary number 15 added to it to create a second color. Add the denary number 15 to the binary number this and give your answer in binary. Perform the addition in binary. Show your working. Okay, so first we need to convert this denary value 15 to binary. Otherwise, we can't just simply add a denary value to binary value. So in order to do that, we are going to divide throughout by 2. So 2 divided by 15, we'll get 7, remainder 1. Then 2 divided by 7, we'll get 3, remainder 1. So 2 divided by 3, we'll get 1, remainder 1. Then again 2 divided by 1, we will get 0, remainder 1. And we will stop when we get 0 over here. Then we will go from down to up and write our values from left to right. Okay, so it'll be like this: 1, 1, 1, 1, and then 0, 0, 0, 0, because we need 8 bits over here. So we have to fill the rest of the empty places with 0. Then we're going to add this value with the number given in the question, the binary number given in the question, which is 0, 0, 1, 0, 0, 1, 1. Okay. So 1 plus 1 is 0, 1 carry. 1 plus 1 plus 1 is 1, 1 carry. Then 1 plus 1 is 0, 1 carry. Then 1 plus 1 is 0, 1 carry. 1 plus 0 is 1, 1 plus 0 is 1, and 0 plus 0 is 0, and 0 plus 0 is 0. So our final answer is 0, 0, 1, 1, 0, 0, 1, 0. Part 3. Hexadecimal 23 in 2's complement representation is 0010011. The denary number 10 needs to be subtracted from this value. Subtract the denary number 10 from the 2's complement representation of 0010011. Give your answer in binary. Show your working. Okay, so in order to subtract the denary number 10 from this binary number, we have to convert 10 to binary. And in order to do that, we'll divide it throughout by 2. So 10 divided by 2 is 5, 0 remainder. 5 divided by 2 is 2, remainder 1. Then 2 divided by 2 is 1, remainder 0. And then 2 divided by 1 is 0, remainder 1. And we will stop when we get to 0. And we will write this representation from down to up and left to right. So it will be 1 0 1 0, and we'll fill the rest with zeros because we need the answer in 8-bit. And then we will convert this into 2's complement, because right now this basically means 10. This is a positive value. We need a negative value. So in order to do that, first we'll put the 1's complement over here, which is flipping the numbers. So all zeros will become 1's and 1's will become 0's. So this is 1's complement. Then we will add 1 to this value to make it 2's complement. So 1 plus 1 is 0, 1 carry, 0 plus 1 is 1, then 1 0 1 1 1 1. Okay, so this is after putting the 2's complement. Now this number basically means that it is negative 10. So we can easily add this binary number to this binary number. So let's just add these two numbers. Okay, so 0 plus 1 is 1, 1 plus 1 is 0, 1 carry, 1 plus 1 is 0, 1 carry, 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1 is 0, 1 carry, 1 plus 1 is 0, 1 carry, 1 plus 1 is again 0, 1 carry, and this carry 1 will be discarded. So this is the final answer: 0 0 0 1 1 0 0 1. So the answer in binary: 0 0 0 1 0 0 1. Part D. Anya made sure that the image was not subject to any copyright before scanning it. Describe what is meant by copyright. Okay, so copyrights are formal and legal rights to ownership. It protects against unauthorized reproduction of work and provides for legal right to redress. Question 2. Bingwen's computer comes with an operating system and utility software. Part A. Draw one line from each utility software to its correct description. Okay, so we have a disk formatter over here, and defragmentation, then backup, and disk repair. Okay, so disk formatter basically sets up a disk so it is ready to store files, and defragmentation moves parts of files so that each file is contiguous in memory. Then backup it creates a copy of data in case the original is lost. And disk repair is here. Scans for errors in a disk and corrects them. So these two options are extras. We don't need them. Part B. Identify 4 key management tasks that operating system will perform. Okay, so the first one can be process management. Then the second can be file management. Then the third can be security management. And the fourth can be memory management. Question 3. A processor has one general purpose register, the accumulator, and several special purpose registers. Part A. Complete the following description of the role of the registers in the fetch execute cycle by writing the missing registers. So we have to fill in the blanks over here. It says that the dash holds the address of the next instruction to be loaded. So it is the program counter. The program counter holds the address of the next instruction to be loaded. This address is sent to the memory address register. Memory address register. The dash holds the data fetched from this address, the memory data register. Memory data register holds the data fetched from this address. This data is sent to current instruction register, and the control unit decodes the instruction's opcode. The program counter is incremented. So these are the answers. Part B. The following table shows part of the instruction set for a processor. The processor has one general purpose register, the accumulator, and the index register. So we have a table over here, and they have explained the instructions, and their explanation is right over here next to them. And then it says that the current contents of the main memory and selected values from the ASCII character set are shown over here. So we have a couple of instructions over here, and there the other table there is an ASCII code and the characters, and then they're asking us to complete the trace table for the program currently in the main memory. Okay, so first we will look at the instruction that is LDD 365, and the address is 200. So LDD, we can look over here what it means. It means that direct addressing, load the contents of the location at the given address to the accumulator. Okay, so in order to do that, we will see that the value of 365 is 1. So we will write over here 200 because the address is 200, and the value of 365 is 1. So we will write 1 over here. Next, we have on 201, compare 366. Okay, so what does the compare instruction do? The compare is over here. Compare the contents of accumulator with the contents of address. Okay, so what we have to do is we will compare the value over here in the accumulator with the value over here in the address 366, which is number 3. And 1 and 3 are not equal, so we will just leave this blank. We will just write the address and we will leave this blank. Then we have 202, and it says JPE. Now what is JPE? Oops. Okay, so JPE is over here, and it means following a compare instruction, jump to address if the compare was true. Now we know that the compare was not true. So again, we will leave this as it is. We will just write the address and leave the rest as it is, empty. Then we have in 203 increment accumulator. What this means is that we have to add 1 to the contents of the register, accumulator, or the index register. So we have the value 1 over here in the accumulator. We will write the address 203 and the value will be 2. Next, we have in address 204, store 365. Store, this opcode STO means store contents of accumulator at the given address. So store 365, okay, and this is address 204. So we are going to store this value 2 in 365. This is 365. We will store it over here. Okay, then in 205 we have move to index register. This means move to index register, and we will go over here and check. Yeah, it means move the contents of the accumulator to the given register. So we will write the address, that is 205, and we will move this value 2 to the index register. Then we have at 206 LDX 365. So LDX basically means indexed addressing. Form the address from address plus the contents of the index register. Copy the contents of the calculated address to the accumulator. So what we'll do over here is we have the address 365 and the value in the accumulator is 2. So we will add 365 with 2 and the answer will be 367. So over here in 367 the answer is 65. So we will write over here 206 because this address, the instruction address is 206, and the answer will be 65 because 365 plus 2 and the answer is 367, and the value over here is 65. So we will write 65 over here. Next we have 207 out. Okay, so what does this mean? This means output to the screen the character whose ASCII value is stored in the accumulator. Okay, so the accumulator has the value 65, and over here we can see that the ASCII code for 65, the character is A. So we will write over here, first we will write the address 207 and the output will be A. Okay, next we have 208 jump to 200. What does this mean? It means that we have to jump to the given address. Okay, so we will write over here 208 and we will leave all of this empty and we will simply jump to 200. So this is a loop basically. So we will write 200 over here, and again it says LDD 365. So 365 over here, now the answer is 2 because over here the previous value in the accumulator is 2. So we will write 2 over here. Then we have the address 201. It says compare 366. So if we compare the value from 366, which is 3, 2 and 3 are not equal, so we will leave this as it is. Then next is 202 and it says JPE, which means that we have to like if the following wait, I'll just show you over here. It says Following a compare instruction, jump to address if the compare was true. Since 2 is not equal to 3, we will just write the address and leave it as it is. So 203, and we will leave this as it is. Next we have 202. The instruction is JPE 209. Okay, so this means that following a compare instruction, jump to address if the compare was true. So we know that the compare was not true because the value in the accumulator is 2 and the value that we are comparing with is 3. So 2 is not equal to 3. So we will just write the address over here, 202, and leave this blank. Then the next is in 203 we have increment instruction. So over here what we have to do is we will write 203 and we will add 1 to the previous value, that is 2, so this will be 3. Okay, then in instruction 4 we have store 365. So we will write 204 and store this value in 365, which is this one over here. Sorry, this one. Okay, then 205 we have move to index register. So we will move this value to the index register, which is this over here. Then we have 206, which says LDX 365. So this means that we have to form an address, which is basically address plus the contents of the accumulator, the index register. So we will add 365 with 365 plus 3, which will give us 368, and the answer in 368 is 66. So we will write over here 66. Then we have in address 207 out, which basically means output the value of the ASCII character. So like this 66 is B. So we will write over here 207 and the output value B. Then there is this jump instruction, jump 200. So we will write 208 and leave this blank, and then this will start all over again. We will write 200, and then it says LDD 365, which means that direct addressing load the contents of the location. So the content of the location is 3. So we will write 3 over here. Then we have in 201 compare 366. So now we know that in the value over here in 366 is 3 and this is equal to 3. So we're just going to write 201 and leave this blank. And then it says over here JPE 209. Now this condition, now it is true, because over here it's saying following a compare instruction, jump to address if the compare was true. Now 3 is equal to 3. So we have to jump to 209, which is this, which is end. So first we're going to write 202 because this is the address for the jump instruction. Then we will write 209, which basically means end. Part C. The accumulator currently contains the binary number 00110101. Write the contents of the accumulator after the processor has executed the following instruction. LSL number 2. So LSL basically means that we have to move to the left side, and the number 2 means by 2 steps. So basically this will come over here and this will come over here. So let me write this over here. 1 1 0 1 0 1 0 0. So this is going to be our new value after the instruction LSL number 2 takes place. 0 1 0 1 0 0. Okay. Part 2. The accumulator currently contains the binary number 00110101. Identify the mathematical operation that the following instruction will perform on the contents of the accumulator. LSR number 3. So this basically means that we have to move to the right, 3 places to the right. So this will basically the final answer over here. So if we write this as base 2, for example, 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, and 2 to the power 7. So we can ignore the zeros, and if we add all of these together, this one, this one, this one, and this one, we will get the answer 53. And since this is 1 2 3 4 5 6 7 8 bits, we're going to divide it by 8 and we'll get the answer 6.625, which we need to round to a whole number, so we'll just write 6. And we can prove this like this: 0 0 1 1 0 1 0 1. So they're asking us to move 3 places to the right, and if I move 3 places to the right, the answer will be 0 1 1 0 0 0 0 0, because if I'm moving to the right, this is going to get discarded, and so 0 0 1 1 0 0, and then we have to add zeros over here. So this is going to be the final answer. And if I add the values over here, this is 2 to the power 0, this is 2 to the power 1, this is 2 to the power 2, and the rest are 0, so I'm not going to add those. Even this one, 2 to the power 0, is basically 1. I'm not going to add this. So I'm going to add 2 to the power 2 is 4, plus 2 to the power 1 is 2, which is 6. And the answer is 6 over here also, so it is correct. So our final answer can be written like this: 53 divided by 8 equals 6.625. And we will just write 6, because only whole number is retained. That is it for today, and I'll see you in my next video.